So quick review, we have two types of systems that we deal with in simulation. There's two ways to model systems. You might have reasons why you model the same real world system, sometimes as one and sometimes as the other. And there might be other reasons why you can never imagine a case where one system would be anything but terminating or steady state. So in the case of terminating systems, we're focusing on systems where we care about the entire runtime of the system. We care about data from the start of the system to the end of to data when the system was turned off. And so we better make sure that we set up the initial conditions correctly in our simulation so that the data that comes out of our simulation will be a good model of the real system over the entire time period because we care about the entire time period. In this case, the hard part is making sure that you've got a simulation where your simulation transients, so this rising part, actually match the transients you get in a real world simulation. But in some ways, in terms of the stats coming out on the other end, once you've got a validated simulation model, it's pretty easy. The big question is just how many times do I run the thing? So I need to make sure that my replicates are independent. I need to make sure that replicate measures that come out of these measurements are normally distributed, at least if I want to apply most of the basic t-test like statistics that I have, those tools. And so the only thing really left there is how many replications. So I usually get independent replicates because I'm going to put a different random number seed into the random number generators that run all of these things. So that's why you guys learned how to build random number generators, and then you learned how to make random number generators turn into random variate generators, because behind the scenes, that's all that programs like Arena are doing. So the same seeds that you would put into your random number generators to generate your random numbers, that then would be used to generate random variates, are behind the scenes doing exactly that in Arena. But you don't have to do all of that work because Arena's doing it. But you do have to tell Arena which seeds to use. By default, when you run Arena, then it picks certain seeds. And that's why some of you may have noticed that if you open Arena and you run a sim and you close Arena and then you open Arena again and run that sim, you get the exact same results. And so if you want to make sure that you have independent replications, then every time you rerun that sim, you need to make sure it starts with a new seed. And so closing down Arena and rerunning it is not a good way to get independent data because we're guaranteed that every time you start Arena, it's going to run all your sims with the same seed unless you take special precautions. And so we will we'll learn how to adjust the seeds in Arena very soon, coming up in a future lecture. But so assuming that we do have independent replicates, now how do we get normally distributed? Well, normally the metrics that we take out of the simulation, like the mean waiting time, things like that. So if we have customers and this is the mean waiting time of a customer at the start of the system, they don't wait a lot at the start of the system, but then the next customer waits a little longer and the next customer waits a little longer. And eventually I get a string of customers that all wait a longer amount of time, but at least it stopped rising. Then if I then take all of that data and I take the average waiting time for a customer in the system where I care about the low waiting times as well as the high waiting times, that average is just a sum. It's a normalized sum. And whenever you have sums of large numbers of data, then those sums tend to be distributed as a normal distribution, which is the central limit theorem. And so fortunately, if you're taking data that inherently is a sum, even though the data points inside the sim aren't independent, as you add all those up together, you end up getting a kind of a bell curve out that has to do sort of with this law of large numbers, central limit theorem thing. And so data that come out of our simulations tend to look pretty normally distributed in many cases because we happen to be measuring things that look normally distributed. Now that's not always the case. You can definitely take data out of a replication that is not going to look normally distributed across the replications, but it just so happens that in most of our cases, most of the things we care about are things that end up being normally distributed across the replications, if not within the replications. So if we get both of those things for free, how many reps do we get? And so what someone will do is they'll say, well, I need you to run as many replications so as you can estimate a confidence interval that is no bigger than so much. In other words, they want to know that they want to have pretty high confidence that the mean is somewhere within your confidence interval. And so they want the confidence interval to be small so that they can pretty much guarantee that their mean is captured in a small area. And so they might say that, they could even give it in terms of percent. They might say that I need you to give me a 95% confidence interval where the width of that confidence interval is no greater than 5% of the estimated mean. And so that would mean that the center of the confidence interval, that sort of sets your base point, and if you were to divide the half width by that mean, then you would get no more than 5%. So that might be a criteria. But so somehow you set the maximum width of your whole confidence interval, I'm calling that 2 epsilon, and then that gives you a maximum width of your half width, which I'm just calling epsilon here. And so since I know the formula for half width, I can then solve for the number of replications that will make that true. And that involves a critical t value that depends upon the number of replications, but I'm trying to figure out the number of replications, so it's not really fair to have that in there. So I'm going to assume that I take enough replications that, again, that t distribution is approximated by a standard normal, and that's where I get this formula. So even if you didn't get all of that derivation, just know, if you can remember, that there is a formula, and it looks like this one, that represents the number of replications you need in order to achieve a half width of epsilon, given an estimated standard deviation of S naught, then that's the formula you need right there. And so if you've taken R naught observations in order to estimate S naught, and then you just need to take R minus R naught more observations in order to hopefully bring your confidence interval down underneath epsilon. And most of the times that will work, but if it happened to be that your R naught observations gave you a really poor estimate of S naught, or maybe your data aren't normally distributed or something like that, but let's just assume the problem is that you only took a few R naught, so your S naught was not a very good estimate of standard deviation, then it might be that after you do all of this, even after you take R observations, you still don't quite meet the half width requirements of epsilon, and so you might need to do this again. But at least in the second round, you'll now have a better estimate of S naught, and so you usually don't have to do this more than, say, 2 or 3 times in order to get your half width down within the epsilon. So that's what we deal with the terminating simulations, is how many reps do we need. So now, steady state systems. So in a steady state system, all we care about in the real system is what the system does after its transients die out. So that means that the benefit of that is that we can have transients in our real system which have nothing, we can have transients in our simulated system that have nothing to do with what's going on in the real system. We just need our simulated system to match our real system in the long-term behavior, sort of in the infinite time behavior. The upside to that is then that might mean that we don't need to model as much as we would need to model in a terminating simulation. In the terminating simulation, we have to get everything right. But in a steady state simulation, we only need to get the long run behavior right, and it's okay if the transients don't quite match. The downside of that is that now we're going to generate data which is totally irrelevant, and before we can generate a performance metric, we need to figure out how to get rid of that data. And so we're going to refer to this as an initialization bias. So this initial data has nothing to do with what goes on in the real system, and so if we include it in the data set that we use to estimate a performance measure, then our estimate of that performance measure is going to have bias due to this initialization period. So irrelevant data is going to create a bias. And so we are going to then compensate for that with a warm-up period where we get rid of this data and only keep the data after that. And that sounds good in theory, but that means we need to figure out how long to make this warm-up period. And so we mentioned last time that you again can run pilot data, and so you can run a pilot experiment and try to figure out, from the performance measures coming out of your pilot experiment, how long until it looks like transients, things that were only happening at the beginning of the sim, stop happening, so that things that happen in the kind of long-term behavior are all that's left over. And so once you've determined roughly where that breakpoint is, in the discrete time, that might be, I'm going to discard D samples at the beginning of my sim. In the continuous time, I'm going to discard, say, T naught time in the beginning here. Well, now that I've discarded data, I don't have that much data left over, and so I need to run my sim for longer to compensate for all of the data that I've discarded. And because I really care about getting a lot of data from the good period that represents where my system should match the behavior of the real system, then I am going to make sure that I have a lot more good data than discarded data. And so in the discrete case, I can just take the number of samples left in my simulation, in my single simulation run, and I will make sure that that is at least 10 times the number of discarded samples at the beginning of the simulation run. This is just in a single run, in a single replicate. In the continuous time case, if I've chopped off T naught at the beginning of each, I'm going to make sure that the entire sim runs for at least 10 times that. And so this is just a rule of thumb. And so the big thing to remember is you basically want the sim to run, you want to have, roughly 10 times as much real data as discarded data. And, those of you that are, particularly sharp are going to notice that, well, why is it N minus D here and not TE minus T naught here? And I'm just going with the convention that your book uses, because again, these are rules of thumb. When you leave the class, as long as you remember this sort of convention that I want roughly 10 times as much good data as bad, that should be fine. That should suit you well. All right, so once I've got that, then I need to say, all right, so that's my single replicate. So how many replications do I need? Well, at this point, now that you've discarded the data, you can treat this like it is a terminating system or a transient simulation. And so you can then go back to the terminating systems formula back here, and you can say, all right, what half width do you want? All right, if you give me a half width, I will give you a number of replications out, and that is going to work for the steady state replicate as well. So this formula right here, even though we designed it for terminating simulations or transient simulations for terminating systems, it also is going to work for our steady state case, so long as we made sure to get rid of this initialization bias. Now, you might find that the number of replications goes up higher than 25. Now, once you reach 25, if you want to make a large decrease in your half width, it's going to require far more replications than are going to kind of justify. You get diminishing marginal returns, and so going from 10 replications to 20 replications, you get a lot of improvement. Going from 20 replications to 30 replications, you don't get quite so much. So instead, what we say is, well, if you have the computational budget where you have the time that you can run more than 25 replications, then it's actually, you're going to get a slightly better performance by running fewer replications, but running every replication longer. So instead of increasing the number of replications, we're just going to increase the length of the sims in a very particular way. And so if we initially ran R0 simulations and we estimated that we need to run R total simulations, so we ran 10 simulations and we want to run 100, rather than actually running 100 simulations, or actually do the 25. Let's say we ran 25 sims and we decided we wanted to run 250 sims. Well, rather than actually running 250 sims, I'm just going to run all of those 25 sims 10 times longer, or at least have 10 times as much discarded data. And so then over here, this is running them 10 times longer. So I'm going to run the sims, each sim 10 times longer, and have 10 times as much discarded data per replication. I still only have 25 replications, but every replication is run longer. Now, it may seem like that is going to be, I may as well have just run more replications. But it turns out that this approach will be better because it further reduces any initialization bias. And so that's why we prefer doing it this way. Once you have enough replications, we prefer to do it this way because the additional discarded data and the additional data collected per replication is going to further squash any residual initialization bias, and it may actually reduce the variance along the way. And so increasing your data in general is going to reduce the variance, but then also getting rid of this initialization phase is going to reduce the bias. And so just in general, we're going to get better and more confident estimators because we've grown the number of data points per replication and discarded more of the problematic data points. All right, so I hope that makes sense. This is a quick summary. It's always better to run more replications because that's going to collapse your half-widths. But once you get up to about 25 replications, then for the case of steady-state systems, it's better to put the investment into growing the amount of discarded data per replication than it is growing the number of replications. So that's all we're doing here. Is that instead of running more replications, we're running a single replication longer, and we are not only getting more total data, but we're also discarding more data. And those two things together, getting more total data squashes variance, and getting rid of the initialization phase, getting rid of more of it, is going to squash that bias. So this is a really nice trick to reduce your confidence intervals by squishing the variance down, but also reducing bias. So this is like the gold standard is to be able to run enough replications, then you can get into this mode where you can run each replication super long. All right, so last thing to make sure that we've covered up before we move into new stuff is this idea of batching. And so this is different than modeling batching in, say, production or inventory systems, which is probably where most of you are most familiar with using that term batching. In this case, we're actually batching individual, bits of data points in a simulation. So the idea here is that we would like to, instead of running 25 replications where every single one of those replications has a long initialization phase that may take a long amount of time just to get to the end of the initialization phase, and then you're just going to discard that data, and then you have to do that 24 more times once you finish the end of that replication, and you restart and do a new replication. We would like to somehow be able to run one replication for so long that we only have to discard data once at the beginning of that replication, and then the rest left over, if there's enough of it, if we chop it up into equally sized pieces, then each piece can actually act like a replication of an independent simulation. And that only works if the pieces are very long. So it's a nice thing about steady-state simulations is that it's kind of like when particles of gas come to equilibrium in a room, then their positions end up not being predictive of their future positions. So if you haven't reached equilibrium, if you've just puffed a bunch of green smoke in the corner of a room, then you can be pretty sure that a second later that green smoke will be farther out in the room, and a second later it'll be farther out in the room. But eventually the green smoke will fill the room, and the whole room will just seem like it has a tint of green. And at that point, knowing where the green smoke is doesn't tell you anything useful about where the green smoke is going to be next. It's just always everywhere. And it's the same idea here, that as long as you discard enough data, then you put the system into a mode where, at least from, there's no long-term correlation anymore. So in the green smoke example, if initially the smoke was in the corner, and I would know that an hour later the smoke's not going to be in the corner. But if initially the smoke filled the whole room, an hour later, I wouldn't know I would know the smoke filled the whole room, but I wouldn't have any useful predictive info about the change in the smoke. So because there would be, in the case of when the smoke all started in the corner an hour later and it filled the whole room, I've now been able to predict a change. There was a variation in where the smoke was, and I could predict it by knowing that as time moved on, the smoke expands throughout the room. But once the smoke fills the whole room, then I don't get any information from the time past about how the smoke changes in the room. It changes just sort of totally randomly. And that's the whole point of steady state, is that if I discard enough data, then long-term correlations fall away. And so if I make these batches long enough, then I guarantee that any data that I find in batch 1 is not going to predict much that's going on in batch 2, and so on and so forth. And so in one replication, I can generate the output of a bunch of different replications. All right, so go back to Canvas, and I'll have a couple of questions for you about this review material, and then we will move on to actually getting to relative performance, where we use a lot of this two-sample methodology.